Some of you have already heard this, but for those of you who just joined in last minute, obviously, welcome to the webinar related to obviously various tube and rod reducing and shaping equipment, which will obviously be the focus point will be on rod mills, drawbenches, and drawblocks. I'm Thomas Mushrow. I'm the product manager for our engineer product components, which includes all our custom equipment, including obviously the items we're going to be talking about today. So I'm going to be giving you guys a technical rundown on obviously on basically just give you some general background on basically what's needed in selecting based on your needs, the various equipment, their purposes, and some basic elements on the analysis. At the end of this, we can obviously shift to any questions you guys have. And as mentioned previously to some of you, if there's questions you have that are a little bit more personal or specific that you guys that you don't want to talk more privately, we obviously can set up either through emails, phone calls, or Teams calls separately to go over those with you guys more personally. So obviously we're gonna just start into this. So as I mentioned, our topics for today are going to be focused on basically the three types of equipment you typically see when we're talking about rod and tube equipment, which are your mills, your drawbenches, and your drawblocks. So when we talk about the rod mills, they're going to be a little bit more. We're going to talk a little bit on the idea of 2 high versus 3 high rod rolling, as well as just some general criteria to give you some background for what basically comes into the sizing nature of working on the mill, which for some of you who might have been on for the strip discussion will have some similarities you'll notice. And then we'll get into drawbenches and drawblocks, which will have a lot of overlap. So we'll talk a little bit about the nature of obviously what comes to deciding a mill versus deciding one of those pieces of equipment. And then we'll then get into more the nature of the sizing of those the drawbenches and drawblocks, and then the various different types of components, gripper types, lubrication, etc., that you can decide between when it comes to both drawbenches and drawblocks, and obviously what drives the difference between the two of them based on your needs. So what you see here is a video that I'm going to do a quick rundown on to give you guys a background accordingly on the just an example of some types of drawbenches we've done in the past. So this drawbench itself is actually a multi-draw drawbench, so it's a little bit more production oriented. So it's running 4 tubes at once that are using a mandrel for controlling the ID. We have support lifters that are coming up that support it as it's drawn, and then self-release it. You see here on the sides. We're going to show this, just give you guys a few different angles. So this gives you a little bit better view of the obviously the lifters as they come up to support the material. In this process, obviously this is a decent amount of pull force, about 24,000 pounds is needed. So we have a hydraulic gripper that clamps down the material that self-actuates, drives it, and pulls it forward, and then self-release in order to actually pull it through the die using a cylinder in the back, and then self-releases it at the end accordingly. So that's just to give you a quick rundown on an example of one type of drawbench we provide in the past. This next video, just a quick rundown, just to give you an example of a little bit more of a simple draw block, just to give you some examples of stuff we've done in the past as well. So this one obviously on the primary difference, which we'll talk about a little bit more on drawbenches versus drawblocks, is the nature of obviously short length versus much more continuous. Drawblocks themselves obviously are used for running much more continuous length material for higher production purposes. This one is running relatively low pull forces, so we used a manual gripper initially for threading and a pneumatic hold-down roll to apply grip and tension. This does run continuous lubrication, but obviously in this video when we're doing tests on the floor, I was manually applying a little bit of it. We're taking off a brake payoff and then running around the drum. Depending on how much is needed to be collected, we will put them in line with other types of equipment, such as dancers and take-ups. In the case of this one, we were running on just a low enough coil quantity that we were running just extension bars for a loose coil shed and collection material, as you see here. And just as a little point of note, you can see a little bit in the bottom corner, a display screen on the control station. That's a display monitoring of the force, because we actually have a load cell tucked into the die box for monitoring the force of the material that's being pulled through, both from a research standpoint as well as a safety net to protect, to make sure that the expected forces we're drawing at, we're not going far beyond that. Because if we see spikes in forces, that means we know we're getting increased resistance and material in the die, which we can then stop to protect the system before the material breaks. So that's just to give you guys a couple quick rundowns of some types of drawing equipment in terms of both on the bench and the drawblock side. So when talking drawing in general, we pretty much, we work with almost any type of material you can name in almost any type of application. This is just to give you guys a few examples. Obviously, in general, we're talking drawing equipment. We're talking tubes, solid rod and shaped wire. For obviously, like I said, almost any material you can name, from the simples like the steels to the more on the precious metal side, your coppers, your platinums, your silvers, and then you're on the energy side, obviously copper as well as stuff like aluminum, your nitinols, very clear material, medical industry stuff as well, just to name obviously a few different types of materials and applications. So depending on what you're looking to do, we can pretty much accommodate your needs on the material side. This just to give you some general rundown. So as I mentioned at the beginning, one of the things I was going to talk about is basically what dictates whether you want to go for a rod mill versus a drawbench or a drawblock. So the biggest advantage of a rod mill is the nature of that you don't need any draw dies. So if you're using a drawbench or a drawblock, you need a draw die, which means you need to point the material prior to threading it through the die and doing your remaining reduction, which naturally generates scrap. So there's less overall scrap and no pointing required when it comes to a rod mill. So those are the big benefits for doing that on a rod mill point. But some disadvantage on the rod mill is because you're using a V-groove rolling pattern, in general, just either to make your round, to make your diamond shape, or whatever you're doing in your tube and rod, because it's two rolls in contact, you have natural more flow to the cavities because it's two pieces coming together versus one solid fixed die. So in terms of your sharpness on your corners, they're going to be a lot looser, and you sometimes might need to take what we call like a two-step hit in order to actually get that concentricity. So that's usually where the rod mills start to lose their advantages, and that's where the advantages on the drawbench and drawblocks come into. So the drawbench and drawblocks are a lot easier for controlling shape and size because obviously they can keep concentricity, or for shapes that are not just circles, they can get you a lot naturally a lot tighter corner radius for your benefits and your needs. And overall, like that's why for a lot of applications you see drawbenches and drawblocks used, but there are a few in particular, like I said, that depending on what the customer is looking to do, that rolling mills can be used quite effectively. And then obviously the nature of a roll versus a draw die will also create a little bit of a difference from a metallurgical standpoint in terms of work hardening and grain structure. So certain customers and certain processes might find that they prefer a certain process based on the grain structure they get in the material, but that's much more obviously customer and application specific. And then, as I mentioned, the drawbenches and drawblocks, they function on the same premise. It's pointing, it's a gripper, it's pulling through a draw die, and it's reducing continuously through the draw die itself while possibly running some type of lubrication. So they work on the exact same basic premise, as well as the way they reduce affects material the same way metallurgically and the process-wise. It's pretty much what decides whether we go to a drawbench or a drawblock is on the premise of fixed length versus continuous. Drawbenches are great for running short length material. Drawblocks for higher production, or where you have the ability to run a full coil of material. That's when they come into play and are getting used, and they're obviously used then much more on the high production end or applications that allow you to run much larger volume at once. So obviously, as I mentioned, when it comes to drawbenches and the drawblocks, you need to point. So there's a few different types of pointing equipment, which primarily you'll see are roll pointers, push pointers, or swagers. We can provide any of those, but I would be remiss to say that obviously we specialize and we make a lot of swaging equipment with various tooling, feeds, and various things. So primarily, if we are requested to provide a type of pointing apparatus with one of our benches or drawblocks, we primarily provide swagers unless requested otherwise. So for those of you that are also interested in pointing equipment to go with drawing equipment, you can also speak to us on the swager front, which we've had a separate webinar, and you can find a video rundown on that online. So now I've talked obviously about just generally surface level stuff on rod mills versus drawblocks and drawbenches. So now I'm going to talk a little bit more, give you some background on the rod mills. Obviously, the photo you see here is an example of one of the rod mills that we ran. This one was running a diamond shaped pattern in the profiling, and obviously you can see that we were running multi-stage hits through the rolls themselves in order to create the reductions over time for the schedule that this customer needed to reach their end application. This one you obviously see has 3 rollers, which is the 3 high configuration, which we'll talk to you about on the next slide. So on rod mills, primarily, there are a few exceptions, but primarily when we're talking about rod mills, we're talking about 2 high and 3 high. The reason being is that 2 high, and because that pretty much compared to strip and other type of applications, these are the 2 configurations that I would say cover almost all, if not all, of rod rolling applications for the most part. Too high is the standard that you see for the most part. It's used for both of them are used for both hot and cold rolling. But the primary benefit that you see usually when 3 high comes into play is if you are trying to get some level of production out of a rod mill, but you're running a fixed length material. With a 2 high mill, you can reverse it back and forth. You can attach winding equipment if you do have full coils of material to run on a higher production standpoint through a single groove slot and then rethread it through. But if you're running a single bar that you want to pass through and want to get the most efficiency out of, the 3 high mill by nature, as you can see in the image, allows you to pass it up through the top rolls in one direction and then pass it back through the bottom 2 rolls in the other direction, allowing you to continuously pass it back and forth without having to stop and reverse the mill. So it eliminates that step. But the moment you do a step where you pass it back and forth naturally or not stopping and reversing, you're not running production quality, you're not running things like that. So 3 high mills are commonly seen for guys trying to get the most efficiency out of a rod mill when they're also very limited in their part length. So thus they're just trying to minimize their downtime between passes so they don't have to wait for the mill to self-reverse direction. So that's just the basic rundown of 2 high versus 3 high. So outside of obviously just the nature of the 2 configurations, when it comes to rod mills, primarily the things we stare at is the rolls themselves and the frame size in terms of selection. Compared to strip mills, rod mills, you typically find a much larger size roll diameter relative to the housing because the contact surface is much narrower in overall width because we're dealing with obviously round product that we're reducing. So we can take much heavier hits but needing a larger roll to grip it, but don't generate as large a load, so we can get away with this usually a smaller bearing. So when it comes to selecting of the roll size, we're usually taking account the area of reduction and the tensile in order to come up with how much load we're generating, as well as the overall reduction we're taking from the thickness and the sides from a standpoint of contact, and then selecting the roll diameter accordingly. Basic rule of thumb when it comes to roll diameter is that the bigger the roll diameter, the shallower the angle of entry you have as you're reducing it, which makes it naturally easier for your roll to grip. But a bigger roll by nature needs more raw force to create the same pressure. The smaller you roll in terms of size of material, the more pressure you need naturally in order to get smaller and smaller, which makes it difficult for a bigger roll in order to produce that. So small rolls are great for going thin. Big rolls are great for taking heavy hits from a grip standpoint. So usually when we are selecting a roll size for any type of application, whether we're talking rod, wire, or strip, that's the basic premise of what dictates the selection of the roll diameter. So we try to find a diameter that gives you the reduction range you need, as well as allows you to gauge as thin. So we try to thread that difference to cover accordingly. And then from that, we then calculate the loads we expect to generate and size the bearing accordingly that will take the loads to accommodate your needs. A few other things to talk about in design and selection. For those of you that more on the strip mill thing, I talked a lot about different types of features such as screw down controls, such as hydraulics, electric, mechanical hand wheel, and things like that you can use for various sizing and control and adjustments. With rod mills, because we do a lot less precision with them, and the reason being is the heart of what's controlling your shape and size when it comes to a rod mill, it's the tooling itself. It's the profile, it's the geometry in your roll. By basic nature, as you saw in the photo a couple slides ago, we are bringing the rolls down to contact. We're just trying to control, and we're basically just trying to exert pressure and hold them at that position, and the shape and contour in between the top and bottom roll and their male and female relation makes the size. So usually when it comes to the size of the screw down selection, we're either using just a simple hand wheel where you bring it down until you have contact, or a simple motor where you drive it down until you have contact and you more just set it and forget it. You're not making constant adjustments. If you're not creating the size you need with the rolls exerting their pressure, it's usually a nature of changing the geometry of your profile itself than making any adjustments on the mill. Which is why for the most part, when it comes to this designing of a rod mill, our focus is on the rolls themselves because it's their geometry, it's their reduction, it's their grip. All of that is what's critical when it comes to really making the rod mill. That one piece of tooling inside the mill is by far the heart of it when it comes to rod rolling. So we're now going to talk a little bit more on the drawing side of the equation. So for draw benches, we can cover quite a wide range of sizes. We've done benches for very low sizing, about 2-foot draws and 250-pound little pneumatic benches. And we've done benches with hydraulic grippers and chains that can do parts 230 feet long that generated 200,000 pounds, and pretty much everything in between. So when it comes to your drawing applications, we can cover a wide range. And I'd be reminiscent to say that obviously we're a custom design house. So if you're looking to do something bigger than this, we're not necessarily afraid of doing that. We can definitely go bigger. Just this is currently the biggest we've been done upon request. So when talking that range, there's basically three styles of drawbenches we deal with in terms of talking about the premise of what is drawing it. They're hydraulic benches, ball screw, and chain. Usual rule of thumb that I apply is that if the material is short enough in length that we're not worried about floor space, I primarily default to a hydraulic drawbench. The reason why is that your point that then is gripping it and moving back and forth laterally that pull the material in a line is a cylinder directly in line with the material. So it's a perfect straight line draw. You can control the pressure. It's great for controlling your tension. It's very simple, it's clean, and it's great to work. The downside to a hydraulic drawbench is the overall footprint your drawbench takes on a hydraulic one is about double the length that a chain or a ball screw is going to take, because you need your draw length plus the length of the cylinder itself. So if you have a 5-foot draw, you have a 5-foot draw area plus a 5-foot cylinder and the miscellaneous stuff around it. So you probably have more about a 12-foot space, which for a 5-foot draw, that's fine. If you have a 100-foot draw, you probably don't want to use a cylinder for that exact purpose. You're going to be more likely in a ball screw or a chain. So ball screw and chain, they both work on a basic same premise. We have basically a motor and a gearbox driving either a chain or a ball screw that moves a carriage block up and down the track that naturally pulls it. The ball screw or the chain is obviously underneath the carriage itself and obviously underneath the material from a point of draw. Ball screws are much more limited and they're used for more application specific. And the reason being is that you primarily see ball screws for applications where the lengths are too long for us to use a hydraulic cylinder. But the overall forces leave concern with are light enough that the ball screw can take it. If the forces are beyond a certain point relative to the length, we default to then a chain type with the chain and sprocket because they're much more rigid, can take it by default. So what you commonly see is, for the most part, is that for our small, low length precision devices, you'll see hydraulic benches such as the one on the left photo in the video I showed you. And then for long material running much higher production, you'll see chain types. And for ball screws are a little bit more application specific. So that's just to give you a quick rundown of the three different types. In terms of, at least this is what's driving the draw mechanism, but obviously there are other components at play when it comes to selecting the drawbench, such as the grippers, which we'll be moving into next. So, in talking gripper types, there are three types of grippers: manual, hydraulic, and pneumatic for the most part. Hydraulic and pneumatic work on the very same premise. It's a cylinder expanding a set of jaws onto the material to clamp it. So the one you see in the photo hover above, both of those can function as either a hydraulic or a pneumatic gripper. That one happens to be a hydraulic one for reference, versus a manual is obviously a self-closing gripper jaw. Rule of thumb is, if the forces are low enough, we use a manual. It's simpler, it's cleaner, you don't have to run piping, and it's a lower cost. Once the forces are high enough that we're worried about the material theoretically slipping the jaws or the ability to get the jaws off the material once you've done a draw, we then shift to a hydraulic or pneumatic gripper. More often than not, you'll see it being a hydraulic for basically two reasons. Pneumatic basically covers what I'd phrase as a range that's too much for a manual gripper to cover, but not so high in grip force that you need a lot of pressure relative to the size of your gripper cylinder. So it's usually working in a limited field. The other reason is because when it comes to a hydraulic gripper, if you're already using a hydraulic cylinder, for example, on your draw stroke, I'm just going to use a hydraulic gripper cylinder for if I need to have something that's either hydraulic or pneumatic at that point, because I'm already tapping into a hydraulic powering and a hydraulic line. So most often you see is that once you get beyond full forces, where you can get away with a manual gripper, you'll see a hydraulic gripper like the style you see there, and it's most likely going to be hydraulic. The hydraulic gripper itself, you can obviously adjust and control your clamping force as well as the based on your pressure, so that basically balance gripping the material versus over marking it. So you'll have the ability to make adjustments there accordingly. And depending on level of precision and controls, we can either have that be manual or done completely through an electronic control system. So some other common features that you'll see on both drawbenches and drawblocks, and I would say it's pretty much, I'd say universally, you see this on every draw block and the vast majority of draw benches, is lubrication. The nature of drawing material through a die generates a large friction contact. There are rod mills you'll see where some customers will use lubrication as well, but it's not as common just by the nature of having something that is a rolling contact surface versus drawing something through sliding friction. Obviously, sliding friction generates a lot more natural heat. You generate too much heat, you get thermal expansion of the material. You get thermal expansion of the material in the die, it binds up, it creates cracking, you have a high chance of it breaking. So very commonly, lubrication is used, one, to lower the coefficient of friction going through the die so it slides through there more naturally, as well as acting as usually a little bit of a coolant reservoir source as well to take away a little bit of the heat. So lubrication is extremely common in drawing just by the nature of what is used in the drawing process. When it comes to applications, we can do wet drawing, obviously, which is running more of a continuous, usually some type of water soluble oil or other types of lubricants through a recirculating system, or complete dry, such as a powder or other types of more solid lubricants, depending on customer needs. 100%, I'll state though that what lubricant you run is 100% indicative of both the material, what you're doing to it, in your reduction, your process, your speeds, all those factors. So when it comes to, in general, any webinar or anytime you talk to me about any type of equipment, I'll phrase myself as a master of the equipment. When it comes to materials, we're jack of all trades, master of none. As you saw in the earlier slides, I talked about that we pretty much cover any material you can name. So I pretty much I set up a machine, design it for a material, and I test and run it for a few weeks and send it on its way, and then I move on to another material. Customer that maybe works on a specific material for 10 years straight, running that exact process, they'll know a little bit more on that material and its behavior than me by that nature, which is why usually when it comes to lubrication selection, we can give some generic recommendations, but we usually recommend that the customer speak to either lubrication house or we trust their own process development that they've worked on for that material specifically, just by the nature of the customer spends a lot more time with one specific material than we do. So outside of some of the stuff I just mentioned, there's other types of equipment that we can provide with draw benches. So the standards ones we went over briefly was obviously the idea of grippers of manual or hydraulic or pneumatic. We can do with interchangeable tooling and things like that to accommodate different wire, rod, and tube sizes. Some of the other things and I also talked about obviously lubrication in terms of dry and wet, but there are other features that we can provide that are a little bit upon request. Some are more common, some are less common. One of the things obviously I showed in a video earlier was the idea of a multi-draw draw bench. So we can draw multiple bars at once programmatically, or we could do simple single draw like you saw in some of the photographs. When it comes to the die boxes, depending on what's needed, and we can do various things with the die boxes in terms of movement and adjustments as needed to, so a little bit more precision to accommodate the customer needs. That's seen in draw benches. You'd see that it's seen much more, I'd say, often in draw blocks, but you can see them both. As well as there are applications, more commonly, I would say, where it's making more rectangular, square-shaped material, where you're not as concerned about your corner radius, and for metallurgical reasons, you want to use roll contact. That customers will mount a Turk set inside of a draw die in front of a draw bench, and they'll pull it through, and that will basically eliminate the need for pointing, and will serve as another method of reducing. So we can also, for some specific applications, mount a Turk set in front of a draw bench. The reason I don't talk about that usually for draw blocks is if you're running a long enough material that you're using a Turk set, I'm treating that more like a wire shaping equipment with a Turk set and a shedding drum than a traditional draw block. But we have done Turk set mounting provisions for draw benches for a short length material where you're trying to pull under tension and create a square profile, for example. Some other types we can obviously do is with any system I quote or provide, level of automation can go from as manual as it gets with an operator hand feeding it, making all the adjustments, start and stopping it through simple controls, or I can go pretty much almost full automated, such as, for example, in that bench that I showed in the intro video where it's drawing multiple bars at once, it's monitoring, we program in the position so it knows exactly when to stop, then self-releases the gripper at that position, the gripper retracts back, it has lifters come up at different points in the cycle to support the material, and then once the gripper has backed off fully, the lifters lower down to naturally release it into a catchment. And we can also add even additional stuff beyond that, such as parts that automatically load it into the bench and once it's unloaded, can take it to maybe even other steps in the process. So depending on what you guys are looking from a production standpoint, we can do various levels of automation. And then just general features that you typically see provided or stuff we provide, such as safety, obviously safety interlock guarding. Standard we practice is OSHA. We also, depending on what location you're providing to, have done CSA, CE, UL, you name it. So if there's certain safety requirements you need to cover, we'll be providing them, with the baseline being at least OSHA. And then usually when it comes to the idea of data recording and things such as with other types of equipment, we can always provide devices for giving you recording capabilities, in which with the Drawbench, usually that primary point of data that people care about is the pull force. So for example, like in the Drawblock that I talked about earlier, we can also with the benches, we can either use pressure transducers built in the cylinders, or we can have a load cell mounted behind the draw die to give you a direct measurement of the force occurring during the drawing process, so that you can monitor and record that for both safety purposes as well as for research purposes. So that's just to give you some ideas of typical types of things that we can provide with benches outside of the more specifics I went into, such as on the gripper and the draw side. So now we slide over to obviously our Drawblocks, which is the final thing we'll be talking about. As mentioned, obviously our Drawblocks are used obviously once you get to a point where you have a large enough length of material that making a bench to accommodate that on your floor is illogical, and you can obviously run it with a comfort that you can bend it around a drum from a much higher production and efficiency standpoint. So Drawblocks are when you usually get to a point in your wire or rod size and length that you can more accommodate a ability to run it at a higher production rate. So similar to benches and rod mills like I talked about, sizing is everything. With Drawblocks, your sizing is 100% based on the diameter of your drum, as well as obviously the force needed to reduce. So basically when we're talking about winding tension, we'll start with round material, it's more simple example, but in both cases of round material versus flat, your winding tension is directly correlated with the radius that it's being bent around. So a smaller drum naturally generates a much higher tension. So depending on how large your material is, how stiff it is, and how in general, that material will naturally have a certain amount of resistance to wanting to bend. So we will have to select a diameter that is large enough to naturally allow us to bend it around there cleanly, while not making one that is so large that is, I guess best way to put it, is overkill for your needs, and thus leading to a much higher cost drum that we're having to spin. So for very small, delicate wire, we've wrapped them around 12-inch drums. For much heavier duty applications, we've had drums that are 70, 80 inches in diameter. It all just depends on obviously how big and stiff your material is in order to create a radius that's appropriate to bend it around. So, and to give you guys some background a little bit on this from an equation standpoint, if you're talking about generally wrapping a round wire around a drum, your tension's roughly your tensile times pi over 32 radius cubed over with the radius of your material cubed over the radius of your drum. So that's just to give you a quick rundown if you're trying to estimate how much you expect your tension to be. That's roughly what we're talking about, which is why, like I said, you double the radius of your drum, you're cutting your natural tension to bend it around the drum in half. So that's very critical in terms of your drum size selection. So outside of that nature, when we look at drums, the other thing we're looking at is obviously the pull force needed to pull it through the die. So with that, that's just a direct correlation of your area of reduction times your tensile strength times basically just some conservation factors. So material that's twice the tensile will generate roughly about twice the load. Material that you're taking about twice the area of reduction, they'll take about double the load. So that's usually what comes down to the general sizing of the Drawblock in terms of how big the drum needs to be, as well as what size motor is behind it, acting as basically your point of pull for pulling the material. So obviously, similar to Drawbenches, Drawblocks come with obviously a type of gripper. The grippers work a little bit differently though. With Drawbenches, the gripper is obviously holding it the entire way through the process. With Drawblocks, we have a gripper that basically is used for the first maybe roughly 3 to 7 wraps, just enough that you get enough wraps for tension around the block that we can then apply basically a roller to grip the material and hold it in place, at which point the gripper releases. So the grippers, similar to the Drawbenches, are based on the concept of how much force is required. If the forces aren't too high, we'll use a manual with chain. One is obviously the cost is lower, but especially on a drawblock compared to a drawbench, they keep it a lot simpler. Manual chain is just a simple thread, set up, grab, and then you self-release, you manually release the jaw and take the chain off once you've got your wraps and your tension roll during threading, and you continue on your way. Once your forces get beyond that to the point where you need something with a little bit more force in a manual gripper, obviously we then talk about a hydraulic and pneumatic, where hydraulic is a little bit more common on the same premise of once you get beyond a force limit, hydraulic just becomes a standard. The way these work is that it's not it's the gripper is built into the drum itself. So the jaws itself actuate out through a cylinder, grip on the material. We do then a handful of wraps and then engage the hold down rule, and then the gripper self releases. So that's why I say it adds a lot of complexity, because we're piping and designing a gripper mechanism and everything that actuates in and out inside basically the cavity of the drum itself, in order so that once the gripper is released, it's out of the way for the material to continue to shed on the drum. In addition, the gripper is fixed. So when you're dealing with a hydraulic or pneumatic gripper, because it's at a fixed location, in order to create that 3 to 7 wraps, you either need to laterally, if it's a horizontal drum, laterally move the drum back and forth, or laterally move the die box back and forth. If it's a vertical drum, you need to obviously move the drum itself up and down as you collect, or move the die up and down, because that's the only way for you to actually create natural separation of the wire, because while your gripper stays in a fixed location where it's gripping the end. So that adds a little bit more, obviously, in addition to the complexity of the internals, adds a little other components that are necessary for the motion of the drum as you do your initial threading. And then similar to drawbenches, very common feature you'll see in drawblocks is the load cell, like I said, embedded behind the die that gives you good monitoring of the force during the drawing process, as well as I mentioned to a little bit earlier, lubrication working on the same premise of wet versus dry and continuous oil, depending on what you guys need. And it's extremely common in the drawblocks because in addition to the friction contact, you're usually drawing at much higher speeds. Drawbenches, usually I'm not drawing at a speed probably no more than double to triple the length roughly in terms of per minute, because once you get beyond like 15, once you're under 15 to 20 seconds per draw, you're spending a lot more time in the setup. With drawblocks, I might be drawing at hundreds and hundreds of feet per minute. I might be drawing at 500, 600 feet per minute. Those speeds with friction contact, you're going to generate a lot of heat. So lubrication that's acting much more as a way to cut down friction as well as acting as a coolant source becomes extremely common, obviously, on the drawblock side. So that was my general rundown on the equipment. Up here was just a couple quick questions that some of you guys submitted ahead of time. But obviously, at this point, Annalise is going to be basically allowing people to chime in with questions that you can either type in, or depending on some questions you have, she might also give you a mic control so that you can speak and ask those questions. So we'll start with those. But if there are people waiting to formulate, I'll then slide into these quickly that came in ahead of time on the question front. Yeah, okay. So most of the, obviously you guys that came in, and I tried to cut some of the details out just for protection. If you guys want to go into details, we can talk now, or we can talk more privately. Were questions obviously related to different types of materials and applications. So one of you guys asked questions about 9-all and titanium, which obviously we can definitely provide that from a linear drawing standpoint. Typically with 9-all titanium, due to them being much higher tensile materials, we usually expect that you'll have a lot larger force relative to your diameter. So most likely those by default, I'm usually using hydraulic grippers with also some type of lubrication. Some of them being dry, some of them being wet, depending on the customer process, but we can definitely provide those with a certain level of automation as well. And depending on this, I know some of you guys less often might also be with 9-all titanium. I like looking to be doing under heat. If that's the case, like I said, we can talk a little bit more privately on that subject matter. When it comes to obviously the next material brought up was some people actually had some interest in drawing some precision aluminum. One of the things obviously you'll stand that is, like I said, when it comes to any material, we can draw it. Depending on how fine you want to go. We've done drawbenches for the medical industry. I've controlled tolerances to tighter than 1 thou on diameter. For some of them, very small and tense. We've done stuff on the drawbench side as well as with our NF swagers for like hypodermic tubing, needles, things like that, where you're more likely to see very small aluminum, titanium, and nitinol components on the medical side of it. So depending on what you're looking for tolerance or the application, we definitely can provide you stuff on that front. And depending on, and that's where I would state when I brought up that we've obviously done little pneumatic benches. That's where you're most likely going to see a pneumatic benches when I'm talking very, very small, like aluminum wire or aluminum tubing or things like that on the medical front, because those are the only times in which the pull force is so low. I can get away with a pneumatic cylinder in my draw front because I'm only generating hundreds of pounds of force versus thousands. So that's where you'll commonly see some of that stuff pop up as possibilities as well. And depending on what you're looking for control, there are various things we can do to monitor the part going in and part going out, at least from a quality control perspective. But when it comes to draw benches in general, from precision, we can obviously, like I said, control tight tolerances. But draw benches and rod mills, more than any other equipment we provide, tooling is huge. With other equipment, we can monitor and make adjustments on the fly to control. But depending on what you're starting and what you're finishing, your die in your draw bench is going to dictate pretty much everything in terms of are you producing the size that you desired, or do we need to make adjustments? But there are definitely things that we can do monitoring that we've done with customers from a quality control perspective that allow them to know when the die is basically fallen past its prime. So we have provided equipment for monitoring that, so once they know that the material is starting to fall outside the tolerance, that it's time to change the die. So we have done things like that because of the nature of how critical the tooling is. Obviously, one of you guys mentioned a desire to draw on the next one, a 70-meter long material rod with 60-millimeter diameter. Yeah, we can talk in more detail on that and dimensions and more specific, like I said. And the answer is yeah, we can definitely provide that. As I mentioned earlier in the slide, we've done benches for 230 feet long. That's about 70 meters. 70 meters, I know, is about 240, but similar in perspective. And we've done rods over 60 millimeters in diameter. We've done ones probably around 75 to a little bit larger in terms of solid material, and significantly larger than that in terms of tube, and that's what's obviously generated those about 200,000 pounds of pull force that we talked about. So, and depending on what you want to do, if you want to go beyond those ranges, it's not something that we're afraid of. We just need to know the numbers so we can plan accordingly. We are a custom design house, so when it comes to any drawbench or drawblock or rod mill we provide, they're not an off-the-shelf item. We're designing them to suit your needs, so they're specialized specifically for your size range to get the best quality of life, as well as give you a machine that will last a extremely long time in terms of rigidity. And then one of you had questions, I see, on converting rod into OTMB shaped wire. Yeah, as I mentioned briefly on the drawbench side, depending on how long your wire is, if it's short length rod that you want to convert into flat wire, we can attach, like I said, Turk scissors or other types of rolls to the front of a bench, so you can pull it under tension, create your shape. If you're running much more continuous length, depending on how sharp your corners are, draw dies can be used. If your corners don't need to be too sharp at that point and you're running a much more continuous length, I would probably treat that closer to more of a wire flattening and shaping type of device, which we obviously would be more like a Turk set in front of a shedding unit, or a Turk set that's self-driven on its own, which obviously we can talk about more specifically, or as well as I'll be going into a lot more detail on those type of equipment during our next webinar on wire flattening and shaping equipment. So that's just obviously answering a few of the questions people had up front.
There's some in the chat box.
But I'm gonna now stop sharing screen to go to ones in the chat box. So one of you asked about experience drawing 6000 series aluminum. Yeah, we've drawn 6000 series aluminum. I would not say that we've drawn it like to a level of any type of specialization, but in terms of aluminum, yeah, I've drawn your standards. I've drawn 6000 series. I've drawn your basically in terms of your alloys in general. For the most part, if you name it within reason, we've at least dabbled in it, because that's what we are. We are a jack of all trades and material. So I've worked with pretty much every grade of, for the most part, aluminum and steel you can mention on the basic ones, as well as then get into much more of the atypical alloys. Obviously, it's nitinols, and we're brought up by one customer, but obviously we also do stuff for those of you that this definitely would be more of a privacy talk, and we'll name customers that deal with stuff more on the energy side with radioactive material and things like that, we also dabble in. So if you have questions on have we worked with that in the past? Yes, and depending on what you want to do, we can definitely talk more in detail about your application, see if that's something where we can assist you on. Obviously, you said for one, Anthony, you said for the draw blocks, when you ask, can a take-up rail diameter be changed out to accommodate for a range of wire diameter? So if you're talking about changing of your ID, within reason, yes. So a lot of times, if you're collecting on a spool, if your ID range isn't too large, we can run a single shaft that works with any bore on the works with the same that we basically would just have to have maybe an auxiliary tool to accommodate if your spool bore changes. If your ID changes dramatically, we have done applications within reason where basically the shaft that either the spool, or if you're collecting on a drum with and thus banding the material, we've done basically a shaft where you can take it off and change it. But usually what I would say is we try to limit that range. So for guys running, that's usually for guys running very small to mid-sized diameter ranges. If you're running a very, very large ID, and by very large, I'm talking about the guys running like 25 to 40-inch ID coils, I'm not designing usually a take-up that then takes an 8-inch ID coil, but I can do a take-up that takes a 4-inch ID coil and also takes a 12-inch ID coil, for example, by having an interchangeable shaft. So depending on what you want to do on the collecting size, yes, we can do that. It just depends on how much you're looking from production and things, whether we make it an interchangeable piece or depending on your range, we can maybe make it something where it's more of a, especially if it's more of a coil form, where there might be just a sleeve that you have on your spool or drum when you put it on there, that makes it so you don't have to spend as much time doing a change for efficiency's sake. But yes, we can definitely accommodate a variety of diameters on a single size take-up. So then obviously one of you also had questions on process development. So process development, I will obviously state, it's ultimately the responsibility of the customer, because like I said, we're a jack of all trades on material, but we are master of the machines, and we are not people that leave customers high and dry on process. There are things that obviously we will that we can do up front with customers in terms of some level of development, but that we'll do obviously prior to shipping, just to work out some kinks. But depending on how much process development a customer wants to do, once we get across their point, obviously, if they want us to continue to system on it, it would just be a standard charge at our rates for our guys' time. But even once the machine's in a field and you guys are having it and you're messing with it, if you guys mess and do some process development and messing with different things and are seeing different results and have some just general questions on things you're seeing, I'm always a phone call away, or some of our other people as well, to maybe answer some questions that you guys seeing and maybe also help still guide you along. So although the process development we always state is responsibility of the customer, we're not ones that will just wipe our hands once you ship the machine and say, your job to worry about it. We obviously want to support you. We want to keep you, help you as much as possible. It's just why we draw that lines, like I said, is I can give you basically, based on things you describe and see, I can provide my expertise from when I've seen stuff like that before. But once you get very deep into the metallurgy of a certain material, that's when you start to fall outside the expertise of me or other people at FENN. And that's when it's more likely why we call it, where your guys' expertise on material needs to come in for the closing of the process development. But yeah, we can definitely provide a certain level of assistance on the process side. So if you guys have any other questions, let me know. Otherwise, like I said, we can end this. Annalise will obviously, for any of you that want it, can provide you my direct contact info. So you can contact me or one of our account managers accordingly if you want to talk more application specific. Yeah, Mark, we've enabled that if you want to unmute, you can talk.
Yeah, there we go. Okay, now it's letting me unmute. All right. So quick question. You mentioned that on your precision tubing, you work under 1,000 kind of number. Is that a function of like the ratio of it, is that a function of the diameter? I guess is the question, right?
When I was talking about that, I was talking about tolerance on the diameter. So like I've done tens of thous for tolerance on your OD, and for ODs I've done stuff that's only a handful of thou in diameter for stuff that's obviously very light and delicate on the medical side in terms of overall OD of the product. And yeah, it's when it comes to that level of tolerance accuracy and things, a lot of it's dependent on the draw die as well as lubrication. And then the final thing is obviously on the material side. Rule of thumb in general, when talk about anything, when you're talking about metal forming or metal reducing, quality you put in correlates to quality you put out, get out. Simple way to phrase that is in a little bit more of a technical ways. Roughly speaking, usually you improve tolerance by about 50%. In general, when you're doing rolling equipment, with drawing equipment, you usually can do a little bit better than that, but there's still a percent limitation. So for customers of mine, I know I've much more commonly on the medical and precious metal side that like say, hey, I want plus or minus 0.0001 inches on my diameter for control, for example. I'm going to advise them, well, your diameter going in has to be pretty tight as well. You can't give me material that has a 3 or 4 thou variation in diameter. Expect any single draw die for me to then get that tolerance. But if you start with that level of tolerance, I could over multiple draw dies slowly improve it to get to that level. Obviously, I went in a little bit of a tangent, so you might have obviously more.
No, that's fine. And so OD, OD fine precision tolerance. I think a lot of us can understand how you achieve something like that, right? Question becomes really one of ID, right?
Yeah.
Go ahead.
Yeah, so ID control, depending on how tight your tolerance is in ID, that's going to be usually indicative of what you use in your drawing process. So for tubes, obviously, as you mentioned on the ID side of it, if your tolerance is loose, we can draw tubes with nothing in the center. But for a lot of guys, obviously, the ID is critical. It's their tolerance on it's tight. So they'll use either floating plug or a mandrel are the two most common. And mandrel, depending on how you define it, can either be something just at the cavity of the die, or it can be an example like you saw in the video of literally an entire rod shoved through the center of the tube. And basically what that serves as is as you compress the material down, material then compresses onto something of a much higher tensile than it. And that basically that stops it from going below a certain ID. So that becomes a little bit on the process development of making sure you whether or not you need exactly speccing out your mandrel. But yeah, we definitely have worked and assisted customers on finding mandrels that work to suit their needs when it comes to tight ID control. And depending on processes, some mandrels line there a little loose so that they're a little easy to insert and retract. For that video, those guys' ID tolerance was extremely tight. So that mandrel was basically pressed into the cavity of the tube before it was even pulled through the bench. So that they needed, basically, we then added tooling on the other side after they were done that allows them to then extract the mandrel from the tube once they're done drawing because of how much pressure we needed to keep in there in order to control the tightness of the ID. So obviously one of you asked on derodding. So yeah, I can probably provide a little bit more information on derodding. Yeah, that's another feature that can be provided. Depending on application, some customers will have derodders that they'll buy separately from us, but oftentimes we'll do derodders as basically what refer to as an attachment onto a drawbench. So we'll basically add a secondary vice grip that basically holds the material in place while we pull the mandrel out of the die or the rod pull the mandrel out of the tube or the rod out of the tube, and then basically have some catchments for when it comes out for the energy release. So we usually provide those as attachments to our bench, but depending on some customers and their level of production needs, they might buy some more commercial derodders that they have on the side. But if you are interested in derodding, depending on what you're looking to do, we can definitely assist you on that. All right. Obviously, you guys don't have any other questions. We can wrap this up here. I know obviously you guys also have other things you need to do on in the day. So it was obviously a pleasure talking to you guys. And obviously, like I said, if you have any questions, you can contact me personally or send something through our sales site, and Annalise will pass it on to the appropriate person to talk to you depending on your application. So like I said, my specialization is in your custom equipment, which covers a wide range of things, but we also have product technical people that specialize more on the swaging side. I have a lot of background on that, but we have one person a little bit more specialized in that than me, as well as on stuff like our spring making equipment and a few other things. So if you have questions on certain types of equipment in general, you're not sure it's appropriate to send to me, you can send it to Annalise, and if it is for me, she'll pass it on to me. Otherwise, she'll pass it on to the appropriate person. All right, it was thank you guys for joining on this, and I hope you guys have a good day.